Hello, class. Welcome to the next chapter in our Advanced Quantitative Methods for Applied Economists course. Today we're going to talk about ridge and lasso, or uh, broadly speaking, regularized regressions. So let us first start with some preliminaries. We need to talk about overfitting and what it means. So in econometrics, there's this thing we call the kitchen sink, right? Doing a regression with the whole kitchen sink, it means you just put in all the variables that you have in your data and hope that some of them come out significant. So your linear regression can take as many variables as you want, in principle up to the number of observations that you have. And because we know that omitted variables bias your coefficients, that's what drives you to try to throw in the whole kitchen sink into your regression, right? Now, the only thing that stops us from doing that is that we know that adding more variables, you're going to pick up some spurious correlations, right? And so then if you have spurious correlations, you're modeling the residual variation, or you're mistaking noise for features of the model, or in other words, you're overfitting. These expressions all kind of refer to a similar problem. So why is overfitting so bad? Let's look at it graphically. Because you might be mistaking noise for a signal, or in other words, you can mess up your prediction. So imagine that the data you have are these purple points here. Now you can clearly see that there is some sort of trend there, but there is also a bit of noise. So if you think about trying to fit a model to these points using polynomials of successive degrees, well, you would start with just a constant, so just your simplest polynomial, just c, and that would be this. So here clearly you're underfitting, you're not explaining much of the variation or trend in this data, right? Then, okay, you start adding other variables, you add just x, and then you have a linear variable. Perhaps the next level is to add x and x squared, and then you get something like this because you're able to create curves. And then you try with x and x squared and x3, etc. And at some point, you're going to get a polynomial that manages to match exactly every single point in this data set. And so despite the fact that this model is perfect at fitting exactly through all of the points, actually it is overfitting, because imagine you get another point from that same data set, it'll be somewhere in this area, but it won't actually fall on that line. Here you're mistaking the noise for the signal. Actually, the trend that you're looking for is more something like this. So this point illustrates that you don't always want to fit perfectly to your data. What you want to do is extract the signal from the noise. So this is called underfitting, this is called overfitting, and this in the middle is the kind of situation that you would prefer. Now, some of you might say, wait a second, don't we just use adjusted R squared when we are worried about having put too many coefficients into our regression? Yes, that's true. Use adjusted R squared to compensate for the fact that we've added more variables. However, adjusted R squared is just an overall measure of the fit, but it doesn't actually change your coefficient. It doesn't actually change your standard deviations or anything like that. As a reminder, if you don't remember, the R squared is the sum of squared regressions divided by the total sum of squared, and the adjusted one is the same thing, but with divisions by the degrees of freedom. So the adjusted R squared will always be smaller than the R squared, and what shrinks it is k, the number of variables in your model. And so the first solution to avoid the kitchen sink problem or overfitting is just to add fewer variables, right? Okay, and so this obviously brings up the questions of how many variables you want in total and which variables you want to put in. So that's a fairly obvious solution, and we'll come back to it in a second. Because first I want to talk about the second solution, which is kind of a trick, which is that you're going to bias your betas. Now, I imagine all of you are shocked by this. What? We're going to bias the betas? Yes, we are. Why? Because even though bias, yes, is bad in general, it can actually help a little bit with prediction because of this overfitting problem, because of the bias variance trade-off. So in the next few slides, I'll explain why biasing the betas can help a little bit with your prediction. There's a really nice video by Josh Starmer that explains it all, and I took some screenshots of it. You can go take a look at that on StatQuest. So let's get back to our sample. Let's say we have these points, and you want to fit a regression line through them. This obviously is our OLS line, it is the line that gives us the least squared error. So we know that this is the best linear estimator, and we know that the coefficients are unbiased here. So this is great. But now imagine that instead of having all of that data, you only had a subset of that data. And in fact, imagine you only had these two points. So you run your OLS to find the line that fits best. And here, because you only have 2 points, this is for illustration, it's very easy to fit it because you get a perfect fit. So here you have a perfect fit and your coefficients are completely unbiased. Okay, so this is great. But now let's put back these points that we pretended we didn't know existed. Now if we go and calculate the sum of squared errors from all of these points that we just put back, actually the sum of squared errors is really large. And if you imagine doing an OLS with any other of these 2 points, this red line here would not be it. It wouldn't fit very well at all. And that is the high variance that we're talking about. If you were to take a different sample of 2 points from this cloud, you would get a very different slope. So the beta would have high variance. And this is where biasing your beta downwards helps a little. Because what can we do? Imagine just tilt that slope a little bit downward. What happens here? We've really reduced the error that we get computed from the cloud. So we reduce the variance, but at the cost of tilting this slope a little bit. So that is the trade-off that exists between bias and variance. You bias your coefficient a little bit, but it helps you reduce the variance. Now, if you Google bias variance trade-off, you will get this plot that is ubiquitous that shows you that when you get a model of higher complexity, the error takes a U-shaped if you think of the error as being the bias and the variance. So the bias is really high with with the simplest model and really low with a very complex model. But on the other hand, the variance is very low with a simple model and very high with a complex model. And so the optimal model is somewhere here. So the underlying principle of everything we're going to do today is that you can trade a little bit of bias for a smaller variance, and that will help you get better estimates or better predictions. This principle is called regularization. So regularization just means reducing the magnitude of your betas to reduce the variance. Some people just refer to this as shrinkage. Other people refer to it as desensitization. I think desensitization actually makes sense. It's a helpful concept because when you think about it, when you make beta smaller, it just means that your y hat is less sensitive to changes in the x, right? It's a lower slope, so one unit change in x leads to smaller changes in the predicted y, so less sensitive y to the x. So I think that's a pretty intuitive way of thinking about this. However, the most common term is regularization. So to recap, overfitting is bad. Why is it bad? Because it leads to high variance and it leads to bad predictions. So in order to avoid that, we're going to do two things. We're going to have fewer variables, okay, and smaller betas, which we call regularizing. So how do we do that? Well, we do that with what is called regularized regression methods, and those are commonly ridge regression, lasso regression, and elastic nets. Okay, so let's get started with ridge regression. That is usually the first one. It's analytically a little bit simpler. So the starting point for ridge is just the regular OLS. Now, as a reminder, OLS minimizes the sum of squared errors. The sum of squared errors is the sum over I, your observations, of yi minus y hat I squared. Right? If you develop that, it's yi minus alpha minus the sum over all the k's, those are your variables, of beta k times xik squared. Okay, so we call that the sum of squared errors. In machine learning, they call this the cost function, because in all of these methods, they're minimizing something they call a cost function. For OLS, this is the cost function. Now, the first thing we're going to do is we're going to get rid of this alpha because we don't want to talk about it, and we're going to get rid of the units because we don't want to talk about them either. So let us just standardize everything. So everything is demeaned and divided by its standard deviation so that it's standardized. Then the alpha drops out. The second thing we're going to do is we're going to rewrite this as an argmin problem. So argmin over the set of betas of yi minus beta kxk squared. If you solve this problem, you get the coefficients, the beta coefficients of your OLS regression. So how do you regularize your regression? Well, what you want to do is you want to penalize the big betas. You want your betas to be a little bit smaller. You want to tilt those slopes just a little bit, like we saw in the graphics earlier. So how do you do that? You add a penalty function to your cost function. You add a penalty function to your sum of squared errors. So the new cost function is going to look like this. It's going to be the same thing as we had before, the sum of squared errors, plus this term, lambda times the sum of just the betas squared. So you recognize this. This is just the sum of squared errors plus a penalty function for larger betas. So larger betas, either positive or negative because they're squared, are going to make this larger, and so they're not going to be good for the argmin problem. And so this is going to make your betas a little bit smaller. Now, how much smaller? Well, that depends. It depends on the lambda. The lambda is determining how strong your regularization is. Now, note that if lambda is equal to 0, this whole thing disappears, and your problem just boils down to a regular OLS. So an OLS is just a ridge regression with lambda equals 0. Now, on the other hand, if the lambda is infinite, the penalty becomes really binding, and all of your betas tend towards 0. So the bigger the lambda, the more you will bias your betas downwards, the more you will tilt those slopes downwards in exchange for smaller variance in the betas. Now, we can rewrite this problem as a regular OLS with a constraint, with an added constraint. So this is just the argument of your OLS. This is your sum of squared errors subject to the constraint that there exists a C that is greater than 0 for which the sum of the beta k squared is less than that C constant. So this way of framing it is just rewriting. So this way of writing it is the same problem, is just rewritten in a way that is more convenient. It is convenient in particular for graphical interpretation, and then you'll understand how this works. So the graphical interpretation of ridge goes as follows. If you plot an axis with beta 1 on the one hand and beta 2 on the other, you can define here your beta hat. This is the least square of your OLS coefficients. It's a given beta value for beta 1 and a given beta value for beta 2. This being the OLS coefficient, it's the unbiased coefficient. Now, as you increase the bias, you move away from that beta, from that unbiased beta, and you can see these ellipses here. Let's say those define the contours of beta 1, beta 2 combinations that have the same amount of bias compared to the central unbiased beta hat. Now, the further you are, the more biased you are. Okay, now what about the constraint? The constraint was beta 1 squared plus beta 2 squared is less than a given constant. Well, if you've done enough math, you know that this is just the equation of a circle. So this circle here is your constraint of beta 1 squared plus beta 2 squared being less than C. And so where are we going to, so what are the ridge coefficients going to be? They're going to be right here, where you can get the smallest value of bias that also satisfies this constraint. So it's going to be right here at this tangent spot. And as you see, both beta 1 and beta 2 are smaller than what they were in the OLS. So once again, the ellipses are the contours of the mean squared errors as they get away from the unbiased beta hat. The circle is centered on 0 and it defines the allowable betas given the constraint that you have. And so the ridge betas are going to be the least biased betas that still satisfy this constraint. So they're going to be the ones at the tangent. So that was for the graphical intuition. Now, mathematically, actually, ridge has an analytical solution. Just as a reminder, the OLS analytical solution for beta hat is x prime x inverse x prime y. You should all remember that. If not, you would not have passed your prelims. And so the ridge equivalent of that is x prime x plus lambda I inverse x prime y. The I here, of course, being a diagonal. And it's a diagonal k by k matrix with k being the number of variables. So as you see, the beta hats from the ridge are actually fairly easy to compute once you know your lambda. Okay, but then how do you know the lambda? Well, actually, the way you're going to do this is just by trying out lots of values for lambda. So for each lambda, you're going to test how much variance they generate. So how much variance they generate means how well they fit when they're tested repeatedly over different subsamples of your data. And the lambda you choose will be the one that gives you the lowest variance. So the one that consistently gives you pretty good fit over lots of different subsamples of your data. This procedure of testing over different subsamples of your data is called cross-validation. So let's just insist on that a little bit. How do you do cross-validation? Well, here's an example. You split your model into a one subset you call the training data and another subset you call the testing data. So you estimate your model on the training subset and then you test the model on the testing subset. Then you get a measure of how well this fits. And then you change the composition of your training and test data, and you do the same thing, and you get a second measure of fit. And then you do it a third time, and you get a third measure of fit. And every time you have a different set that you train the model on, and a different set that you test the model on, and you get lots of different values of fit that are possible. And then you compute an average of the fit of all these iterations. One of the most common ways to do that is called k-folds cross-validation. It's called k-folds because you divide your total data set into a certain number of subsets that you call folds. So you're going to do a first fake experiment where you take these 4 folds to train your model, meaning to estimate your betas, and then you test the fit on this subset. Then you take these 4 subsets and you test on this blue one, then you take these 4 and you test on that blue one, etc., etc. And so this gives you 5 measures of fit that you can then collapse to one overall measure of fit for the given models of parameters that you're thinking of. So how do you apply that to ridge? Well, you do that for each lambda. So you can think of this kind of as a loop inside of a loop. So for each value of lambda, you're going to run a cross-validation procedure that loops over lots of iterations of your data and gives you an average fit for that lambda. And then you're going to take the next lambda and you're also going to do a cross validation, and that gives you a fit for that lambda, et cetera, et cetera. And so for each of the lambdas, you're going to get a cross validated measure of fit, and then you're going to take the one with the best fit. And that will define your optimal lambda. So there is an entire literature on cross-validation. K-folds cross-validation is the simplest one. It's very intuitive. Everyone understands how it works. There's another one that's very intuitive called leave one out, where you successively leave out one of your observations. You can also have leave P out when you leave P observations out, etc. There's something called stratified cross-validation. There are specific cross-validation methodologies for time series, etc. If you want more information on this, there are a lot of resources out there. But the most common one is usually the k-folds. All right, so let's put this all into practice. We're going to do a little example with some fake data that we're going to make. So this is going to be our fake data set. We're going to have 50 observations, so not a lot. There's going to be some noise with 7 variables. Let's make the x variables. This just makes 7 variables. They're all defined with R norms, so they're all standard normals, and we all call them x1, x2, etc. Then we'll define a y that is actually a constant plus x1 plus x2 plus an error. Okay, so this is exactly a linear model. There are just 2 variables that should matter here, right? x1 and x2. So x3, x4, x5, etc. until x7 should not matter at all. This is what the data looks like. This is our y variable. These are the x variables. Of course, there are 50 observations. Small thing we did first, we scaled them. So we standardized and normalized again, just to make sure that these are all centered on 0 with standard deviation 1. So let's run an OLS and take a look at the output. What you see is that the OLS is, of course, picking up some spurious correlations. So x1 and x2 matter. That's good. That's what we were expecting. But then x5 seems to matter almost as much as the other two. X6 also seems to matter. So here, clearly, we only had 2 variables that actually mattered. But because there's some noise, the OLS actually picked up what it mistook for some signal from these variables x5 and x6. So to explain ridge, I actually find it easier to just do it by hand. So first, let's just do the OLS coefficients by hand, just as a reminder. So here we extract the betas that came out of our lm command, our actual regression command, and then we're going to make sure that we're getting the same coefficients if we just compute x prime x inverse x prime y. So this is pretty easy to do in R, because R has this solve command, and the solve can be used for matrix inversion. So we do x prime x inverse x prime y, just to check that by hand we're getting the same coefficients. And now we're going to do the exact same thing, but with the ridge. So what does ridge do? It's still x prime x inverse, but in the inverse you still have lambda times this diagonal, this identity matrix with a diagonal row of ones over k rows. Okay, times x prime y. These are going to be our ridge coefficients by hand. What lambda value did we choose? We took lambda equals 1. Just as an example, this value is not more meaningful than any other. However, there is a value that is more meaningful than another, which is lambda equals 0. So let's just redo this with lambda equals 0 again to check that we're getting the same coefficients as we should from the OLS. Okay, so what do we get if we just put together these 4 columns? These are the betas that came from our OLS that we run with the lm command. These, just for checking, we did the OLS by hand. They're exactly the same. The ridge with a lambda equals 0, again, they are the same. And then the ridge with lambda equals 1, you can see they are all slightly similar, 0.31, 0.30, 0.64. 0.62, etc., etc. One of them here is a little bit larger. It's the 0.01, 0.02, and we'll talk about that in a second. So we've confirmed that ridge with lambda equals 0 is just a regular OLS, and that ridge with lambda greater than 0 gives slightly smaller betas. So this is the shrinkage or the regularization that we were expecting. So let's see how this regularization works over larger and larger values of lambda. So we make a little function. So this is just a function that we're going to call ridge func, and we're going to give it an x, a y, and a lambda. So for any value lambda, it will solve this x prime x plus lambda diagonal inverse x prime y. So just because we don't have much space on the page, let's do it for 5 values of lambda. We'll do 0, 0.5, 5, 50, and 500. So you see exponentially growing values of lambda. We're going to apply it with the with an sapply command, and we're just going to put them all as a matrix. And so here, what do we see? Lambda equals 0, that's still just our OLS, and then we get slightly smaller values of betas, slightly smaller values of beta still, then again smaller, and again smaller. And so we've reduced our coefficients from some that have, that are at the first decimal, 0.3, 0.6, etc. When the lambda is really big, they become 0.02, 0.05, etc. They become really, really small. So as lambda becomes very big, our beta coefficients are forced to be very, very small. That said, look at this coefficient, number 4. This one kind of stays where it was. It was 0.01, now it's 0.02, then it's 0.03, 0.05, 0.01. So that one kind of reached the limit of how small it is going to be. It's going to stay roughly in this ballpark, at least until the values of lambda get bigger and bigger and bigger, and all these other coefficients also get very, very small. So there's kind of a limit to how small the coefficients can be. In other words, the coefficients never get to actual 0. Now, of course, R has many packages that you can run a ridge regression with. There are several to choose from. Mass, glmnet, and lmridge are the 3 that I tried out here. I'm going to use the mass package with the function lm.ridge, because that one is quite simple in its use. So you feed it a y variable and an x variable. Here you add -1 just to make sure that it doesn't take an intercept, and then you give it a lambda. Here, even instead of just giving it one lambda, we give it a sequence of lambda. So we give it all the numbers between 0 and 100 with a 0.5 at a 0.5 interval. So we get 200 values of lambda that we're going to try out. We're going to call this model ridge mass. And you can plot this model right away. You can just say plot ridge mass, and it gives you this plot. What is this plot? Each of these lines represents one of your betas. And here, the x-axis is the lambda. And so you see that as lambda grows from 0 to 100, all of these coefficients get shrunk, smaller and smaller and smaller. But they don't actually get to 0. They asymptotically move towards zero. And so how are you actually going to choose the best lambda here? Well, you're going to take the one that gives you the best fit. So there's another command, another post-estimation command with this called just select ridge mass, and this gives you some criteria that you can try. The HKB estimator, the LW estimator. We're going to look at this, the GCV, which is the generalized cross-validation measure. It's 6.5. So that is the lambda that gives us the smallest value of the generalized cross-validation. So once you've decided on your smallest lambda, well, then you can just rerun your ridge regression with that particular lambda instead of the whole range of lambdas. Or you can do this automatically with this little command you write, which minimum of the ridge mass GCV. This will automatically select the number 6.5. So we rerun our ridge regression and we look at our ridge coefficients. And so these are our new coefficients with the ridge regression using the best lambda that we could, the best fit. So as you see, these are a little bit biased. They are not the OLS unbiased coefficients, which were 0.31, 0.64, etc. They are all a little bit smaller, but if we are to trust our ridge, they give us smaller variance, so they're actually better for prediction of the values in our dataset. Now you might ask, are those betas significant? Well, that package doesn't actually check that because most of the time, machine learning people don't actually use significance that much. This is all about selection. It's all about prediction. So you don't just write out, is my beta significant? So that's a little unfortunate for us because we really like talking about our betas. In particular, one thing we would like to do is, at least if some variables are completely insignificant, completely useless, we would like to get rid of them and not have them in the regression. And so this works as a pretty good segue to go into the next part, which is Lasso. Because Lasso not only reduces the value of your betas, at some point they hit zero and then they drop out of the equation. So then you can get rid of the variables that really have no explanatory power. Okay, so now we get into Lasso regression. So Lasso regression is almost the same as ridge. Why is it almost the same? Well, because it functions the same way. You also modify our OLS cost function by adding a penalty for larger betas. The only difference here is that instead of adding a penalty for betas squared, you use the absolute value of beta here. So the new cost function is the sum of squared errors plus a penalty for large betas using the absolute value instead of the square. And it is also multiplied here by this lambda parameter, this regularization parameter. And so what looks like a very small difference is actually going to give us very different properties, very interesting properties that actually are the reason why Lasso tends to be more popular than ridge. And to understand why this works, let us first rewrite this cost function as an OLS with an added constraint. So here we have the argument of the least sum of squares subject to a constraint, which is the sum of all the absolute values of the betas needs to be smaller than some constant c greater than 0. And so again, when you write it that way, it's convenient because you can think of it graphically like this. So here again, just as earlier, we have our beta 1 and beta 2 space. This is the beta hat that gives you the unbiased, the OLS coefficients. These contours are the levels at which beta 1 and beta 2 have a certain bias away from the beta hat. And this is our constraint space. This is defined by the equation absolute value of beta 1 plus absolute value of beta 2 have to be less than a given constant c. And so for comparison, this is what we had with the ridge regression. Now the important thing here, the reason why Lasso is so interesting, is because this constraint space has corners. And so your contours are very likely to hit a corner. Now what happens at a corner, at this corner, beta 1 is equal to 0, which means that x1 drops out of the equation and we're only taking into account x2 as an explanatory variable. This is entirely driven by the fact that this constraint has corners. This constraint is smooth, and so here you're much more likely to find tangents, and it's very hard for you to actually hit exact 0, right? But here, this is going to happen all the time. And if you extrapolate this into a multidimensional space, you can imagine that you have lots of variables and they all have this kind of constraint that has corners, and so they're going to be likely to drop out of the equation when the contours hit a corner. So at that point, I can now tell you what Lasso actually means. Lasso stands for least absolute shrinkage and selection operator. So the word shrinkage is because of the regularization, it's making the betas smaller, it's shrinking the betas, and selection because it's setting some of those betas to 0 and thus selecting out the variables that don't matter. Unfortunately, Lasso's analytical solution is a little bit complicated, so I'm not going to go over it here. Ridge was much simpler. The problem is that, of course, Lasso has this absolute value, and absolute values are non-differentiable functions, and so it's a headache. So we're not going to go over it. Instead, let us just look at Lasso in R. How can we run a Lasso in R? We can use this command, for instance, glmnet. So this command is rather simple to run as well. You just run glmnet, you feed it the x variables, this is your matrix, y, this is a vector of your y variable, you tell it that the family is Gaussian, you tell it that alpha is 1, that's just a parameter, and then you give it a set of lambdas. Now there's a small difference, is that the glmnet command understands the lambdas a little bit differently than the previous commands. It multiplies the lambdas by n, so if you want to make them comparable to what we did before, you divide by n here. So you run the command and then you run a plot command on that lasso, and you tell it you want to plot the lambda on the x-axis. So here, this is going to be our lambda. It actually likes to log it. And like I said, the values are a little bit different from what they were before, so don't worry too much about that. The point is that each of these lines is one of your coefficients. And as previously, these lines are gradually getting lower, closer to 0 as lambda increases, but the important thing is that they actually hit 0 and stay at 0 for given values of lambda. And so as you notice here at the top, it's telling you here there are 7 coefficients, still 7, still 7. Now we've lost a bunch, it's dropped to 3, and then by the time you're at this level of lambda, you have 0 coefficients left because everything was set to 0. So as you increase your lambda, your variables drop out one by one, and that is the selection that Lasso does for you. So this kind of algorithm is especially useful when you have many covariates. In the extreme, it's actually used in cases where you have more variables than observations in your data. So that doesn't happen very often in my field, at least, but in some fields it happens all the time. Think, for instance, in medicine, if you're trying to see determinants, genetic determinants of certain conditions, you have a lot more genes in the genetic code than you can test patients, so you have more X variables than observations in your data. And so what does Lasso do at this point? It runs a lot of cross-validations. It loops over the data that you do have to drop out all of the variables that it doesn't need. And that's how you can select only the covariates that matter. Another nice thing that this command does is that it automates this cross-validation that we talked about. So there is a variant of the glmnet command called cv.glmnet. Obviously, CV stands for cross-validation. So you can do the exact same thing we did before. You just chuck a little CV in front of this, and what is it going to do? It's going to run these Lasso regressions focusing on what the smallest lambda might be. So then when you ask it to plot this CV lasso, the lasso that you did with cross-validation, it gives you a completely different look in the graph. Here, you still have the log of lambda on the x-axis, but on the y-axis, this is the mean squared errors, right? This is the variance that you're trying to make as small as possible by biasing your betas. And so what it's telling you here, at each point, it's giving you the mean squared error that comes out with this value of a lambda. And as you see, it dips here a little bit and then it starts growing again. So where is the smallest variance happening? In this line. The program actually gives you this first line. This is where the lambda is smallest. This is where lambda is best according to some other criterion. And again, it's telling you how many variables it's using here. So as you see here, at the point here where it found the smallest mean squared error, this lambda corresponds to either 5 or 6 variables that stayed in your model. And then you know which lambda to use, and you can run another lasso with that value of lambda, just like we did with ridge, to get your new coefficients. So there's a third methodology that is used for regularization, and that is called elastic net. Well, what is elastic net? It's very easy. It's simply a combination of ridge and lasso. So look at this cost function. You still have the sum of squares from the OLS. You still have a lambda parameter, and then you have something big here. What is this? It is just a linear combination of the two penalty functions, the one from ridge and the one from lasso. So it's 1 minus alpha over 2 times the penalty from ridge plus alpha times the penalty from lasso. And so you notice right away, if alpha is equal to 0, this drops out and you just have a ridge. And if alpha is equal to 1, then this drops out and you just have a lasso. And you might have noticed I told you earlier we had an alpha parameter in the glmnet command right here. This is exactly this alpha. You can set this alpha to 1 to get a lasso, you can set it to 0 to get a ridge, or you can set it to something between 0 and 1 to get an elastic net. So the glmnet command does all three: ridge, lasso, or elastic net. So you might ask, what are the applications for us in econ? What particularly might we do with these methods? Well, the first thing obviously is model selection. For reducing the curse of dimensionality, or if you have lots of variables, you can use something like Lasso to select a model with fewer variables when you have too many. The second thing is, as all these machine learning algorithms, for questions that involve prediction, this is going to be good because, again, we are willing to trade off some bias for the power that we have in prediction. And in that case, of course, you're not going to be focusing on the values of the betas as we do in causal inference. Rather, you're going to focus on the fact that these betas give you good, accurate predictions. And a third application might be the problems that we have in econ that are actually embedding prediction questions inside of them. So think of propensity score matching. The first stage of a propensity score matching algorithm is to do the matching, and that is in essence a prediction problem. So what you can do is you can use something like this to improve your matching, to improve your prediction, and then use it for causal inference later. So one of the ways in which these algorithms can be helpful for us is to help us with the prediction parts of our causal inference questions. This field is growing very fast. There's a lot of things to learn about this. If you want to know more, Susan Athey and Guido Imbens are at the forefront of this field. They have written a lot about this, so I suggest checking out their paper here. And also there are some good lectures by Cameron that explain the econometrics of all of these methodologies.